Hi, welcome to part 4 of the video series Deriving Euler's Number. This is the finale. This is when we finally discuss why E or Euler's number is approximately equal to 2.718. So let's start off. We're first going to have a brief look at the two equations we worked on in the previous few videos. The first one is the derivative of a logarithm, which we discussed in detail and derived in the previous video, which says that the derivative of a logarithm is just equal to 1 divided by a constant times b raised to x, wherein y is equal to b raised to x. Okay. And the second equation is from the fundamental theorem of calculus, which we have discussed in a lot of detail in the second video of the series. So let's start off now with the main derivation. What we are going to look at is a situation when x is equal to 0. So if x is equal to 0, this means y is equal to b raised to x, which is b raised to 0, which is equal to 1. Because any value to the power of 0 is equal to 1. Now we'll use both these equations we just talked about to find the derivative of a logarithm at x is equal to 0 or y is equal to 1. So let's take the first one. This is equal to 1 by a constant times b raised to x. And we just saw that b raised to x is equal to 1 when x is equal to 0. So this is equal to 1 divided by c. And this is going to be our first equation. Now the second equation, we'll find the derivative of the logarithm using the fundamental theorem. This says limit h tends to 0. Now here our function is the logarithm of y. So this would be equal to log of y plus h to the base b subtracted by log of y to the base b divided by h. Now if we substitute y equals 1 in this case, then this is equal to this is equal to limit of h tends to 0 log of 1 plus h to the base b minus log of 1 to the base b divided by h. What does this mean? If you look, let's look at the second term over here, the one I've tick marked. It says log of 1 to the base b. B raised to what would be equal to 1? 0. So you can cancel this term because it's 0. Okay, so this entire term is just equal to limit of h tends to 0. And I'm going to write it in a slightly different form. I'm going to put 1 by h on the side times. You'll understand why a little later. Okay. This is our entire term. Now, also, let's try and understand. Let's go back actually to a property we had discussed in the first video of logarithms. So in that property, we said that if we're looking at a logarithm that has a value with an exponent, it is equal to the exponent times the logarithm of that value. And here we have a slightly different, we have the opposite equation with us. We have something being multiplied to the logarithm of a value. So what we could rewrite it as is limit of h tends to 0 log of base 1 plus h to the power of 1 divided by h. Okay? And this is equation 2. Now if you see both 1 and 2, the right hand sides are giving you values of the derivative of a logarithm. So let's equate these two right hand sides. We can hence say that 1 by c is equal to limit of h tends to 0 log of b 1 plus h to the power of 1 divided by h. This is our main equation. Now what we are going to do is, we're going to just take out this h part and analyze it. Yeah, I'm going to write it at the top over here. Okay. Limit of h tends to 0, 1 plus h to the power of 1 divided by h. Now let's have a look at this base. 1 plus h. H is very close to 0. This means that 1 plus h would be very close to 1, right? Similarly, 1 divided by h would be very close to infinity. So what does this mean, this entire equation? It says something that's very close to 1 to the power of something that's very close to infinity. What does that really even mean? You can't directly say that it's 1 because it's a number very close to 1. Now this is where we find Euler's number, the balance between this value, this base that is very close to 1 and the exponent that is very close to infinity is what gives us Euler's number. So this limit of h tends to 0, 1 plus h to the power of 1 divided by h is equal to e. And that's a very cool conclusion we have come to, which we're going to understand properly in the next slide. So let me open it up. I've created a table here. Okay. So you see, I've gotten the equation over here in orange, right? And now let's have a look at what this table says. So the first column is h. We're basically looking at different values of h, and we keep decreasing the value and keep making it closer to 0. So we first have 1, then 0.5, then 0.1, 0.01, and so on. Then we calculate 1 plus h and 1 divided by h, which are parts of our equation, and then the entire equation. Okay, so let's have a look at it. When h is equal to 1, the entire equation is equal to 2. So at least we got the first value of 2.718, the integer part. Then we have a look at 0.5, h equals to 0.5. And we see that the equation has now resulted in 2.25. So we are slowly getting closer to 2.718. So let's decrease h further, make it 0.1, and we see that when it's 0.1, the equation is equal to 2.59. That's much closer. We're coming really close to 2.718 now. So let's decrease h further and make it 0.01. And now this time we see that we actually get the first decimal of 2.718. So let's decrease it even further. Now let's make it 0.001. And this time, if you notice, we get 2.71 as the first three numbers. We are so close to 2.718. So let's decrease h even further and make it 0.0001. And this time we get our number that we approximately know of. We get 2.718 over here. So you see, what happens is that as h's value decreases, the precision of Euler's number increases. Now we in everyday life, we use 2.718 as the approximation. But for people who want to calculate better and more precisely, more decimal values are important in Euler's number. That's why if you notice, even though we got 2.718, decreasing h further gives us a more precise value of Euler's number. So 2.718 keeps staying the same, but the rest of the decimals become more and more precise. Okay. Now let's go back to that equation we had talked about, that 1 divided by c is equal to, now what I'm going to do is I'm going to substitute limit h tends to 0, 1 plus h raised to 1 by h with e. So this is equal to logarithm of b to e. Yeah. And this happens only when y is equal to 1 or x is equal to 0. Okay. Now in this equation, what you'll notice is this. Let's say the base b is equal to e. This means that the logarithm of e with the base e, what would it be equal to? E raised to what will give you 1? Sorry, e raised to what will give you e? 1. So therefore we could say that 1 divided by c is equal to 1 when b is equal to e. This means that c is also equal to 1 when b is equal to e and y is equal to 1 and x is equal to 0. Now if you notice, this also means that the derivative of a logarithm with the base e, and here I'm going to write y. Let me just scroll down a little bit to give us a little more space. Okay. So now what we've written is, okay, d is equal to 1 by c times b raised to x, where both the denominator values are 1. So this is equal to 1. This means that if the base is Euler's number, then when y is equal to 1, the change in the logarithm is also equal to 1, or the slope is also equal to 1, which is a straight line. Okay. This is just an extra piece of information on what happens when y is equal to 1 and the base is also Euler's number. Okay, so that's it for this entire video series. We have finally understood why Euler's number is equal to 2.718. And yes, that's it. Thank you so much, and I hope you all have a great week ahead. Bye bye.